All right, so today's lesson is about electron configuration, the shorthand version, and PES, which we'll get a little bit more into at the end of the hour. So we need to talk a little bit about that right now. But before we jump into that, here we go. So you had a periodic table, or was given a periodic table yesterday, and we kind of like colored some stuff in. We made some boxes around some things. So here is another representation of that. And what I really would like to kind of focus on here, or at least bring to your attention, is that the first two columns of the periodic table, that is your S block. The S block can hold 2 electrons total. Okay, and you don't have this, but you do have that periodic table that I gave you yesterday. You could be writing on if you wanted to. The reddish pinkish column over here, or group over here, is the P block, and that can hold 6 electrons total. And then this yellowish part of the periodic table is your D block, and that can hold 10 electrons total. And then the greenish one on the bottom is your F block. And that can hold 14 electrons total. Now, that's great and all, but there's a little bit more. So what you also need to probably understand or remember is that the number of orientations that each of these have. So like the S block has 1 orientation. The P block has 3 orientations. And the D block has 5 orientations. And the F block has 7 orientations. And the reason why I'm taking time to talk about the number of orientation is because for some of you who've been doing well with this, great. For some of you that are struggling with this a little bit, each orientation is the number of dashes, and we'll touch upon that in a minute, that you would use when you're writing orbital notation. Now, the other thing that I want to highlight over here is this column right here. It's the 18th column of the periodic table. Does anybody know what the elements in the 18th column of the periodic table are called? Stunning silence says you're all screaming out loud inside your head. These are the noble gases. Hopefully that sounds vaguely familiar. The noble gases on the periodic table are the elements on the periodic table that are gas at room temperature, number 1. And number 2, they are considered inert, meaning that they don't tend to react with anything else unless they're forced to. And even some of the ones that are forced to can't react with anything else either. Yes?
So neon's a gas?
Neon is a gas.
How's it called?
It is a, I guess, classification of a type of color, because like neon green is different than green, right? But neon signs are the ones of the gas tubes that like say open. No?
Wait, so what's neon used for?
Neon gas is oftentimes, well, many gases are oftentimes used in neon signs, because when you electrify the signs, the gas inside changes a color and it gives off shapes and things like that.
Oh, so you said the one that says like open.
Like open, yeah.
Is it like a glow stick?
No, it's not like a glow stick.
What's a glow stick?
A glow stick is a chemical reaction between 2 different compounds that when you crack it, you're releasing one of the compounds, and that one reacts with the other one, and it gives off what we call phospholuminescence. Anyway, the Nobel gas configuration. So what this is we've been writing the electron configuration, and we've been writing what's referred to as the longhand form of the electron configuration. And now we're going to take a little bit of a shortcut when we go to write the electron configuration. So the first example that I'm going to do here is neon. And if you locate neon on the periodic table that I told you to get out, which I can see about 3 of you did, okay, you'll find neon has 10 electrons. Now, if we go back up to my handy-dandy periodic table over here, what I really want to point out is where neon is located on the periodic table. It's located in the P block. It's located in the last column of the P block, which tells me that I can predict that I know what it's going to end with, and it's going to end with P6. And because it's in the second column or second row, it'll end 2p6. And that's going to become important in a minute. So if I write the actual electron configuration for neon, I would write 1s2, 2s2, and I would write 2p6. Now, because neon is inert, because neon is a noble gas, because neon doesn't react with anything under normal conditions, we can use any noble gas, but in this question we're going to use neon as a jumping off point for other elements that come after it. So if I wanted to write what we call the Nobel Gas Short Cut, I could simply write bracket Ne and call it a day. Because when I put a noble gas in brackets, we're basically telling anybody in the chemistry world, hey, listen here, the electron configuration for neon is assumed to be 1s2, 2s2, 2p6, but we don't have to write it because neon doesn't react. Okay? And if I wanted to write the orbital gas notation, would simply be that. So I'm not writing arrows, I'm just writing neon bracket. So the neon bracket refers to 1s2, 2s2, 2p6. Now the next element that we're going to talk about is magnesium, which has 12 electrons. Okay. Now, when I write magnesium's electron configuration, and we're over here, so here's magnesium, and because it's in the S block, it's the second column of the S block, I can predict it's going to end S2, and because it's in the third row, I can predict it's going to end 3s2. But if that's the case, I can write 1s2, 2s2, 2p6, and then I'll finish it up with 3s2. Now, what I hope that you can see in terms of things that are similar from neon, the noble gas, to magnesium, the not noble gas, is that there is the noble gases configuration here. So if I wanted to write this a little bit faster or shorter, I can say neon in a bracket, and that will represent this business right here. Okay, but I have to finish it with 3s2. So when that's the case, I've now said to the entire world, 1s2, 2s2, 2p6 is in that bracket, and then 3s2 is really the rest of it. Okay, so I made it a little bit faster or easier to write. So now I'm going to do the same thought process and go ahead and write the shortcut, the orbital notation shortcut, which will be the same thing. Neon in a bracket, 3s, one orientation, arrow up, arrow down.
So then, anytime, any element, are we always going to just put neon?
So the question is, if I wanted to write the Nobel Gas Shortcut notation for any element, do I just write neon and then go from there? And the answer to that question is you could, but that doesn't necessarily make it better. So we're going to go ahead and do a different example. And I guess I'm going to choose one that is still going to use neon first,
Okay.
and then we'll go to something else. Yes.
So let's say you had an element like potassium, right?
Okay.
Could you go bracket, argon, bracket, and then 3s2?
Close. So the question was, could you do potassium bracket, argon bracket, 4s2? And it wouldn't be 4s2, but it would be 4s for potassium, which is K, 4s1.
Oh, yeah, my bad.
Okay. So sulfur has, so sulfur has 16 electrons. Okay. Now, if I locate sulfur on the periodic table, it's right here. Okay. If I go back up to the one up here, sulfur is right here. I can predict that because of where sulfur is, I can see that it is in the P block. It's in the third row. So it's going to be a 3P, and it's going to be like 1, 2, 3, 4. So it's going to be a 3P4. But if I want to make this a little bit faster or less to write, there's a noble gas that comes numerically before sulfur on the periodic table. And that one happens to be neon. Another way to look at it is which noble gas is in the row above the element you're trying to write the electron configuration for. So in this instance, sulfur has a noble gas directly to its right, argon, but it also has a noble gas one row above neon. And we're going to use the noble gas one row above neon because that's the noble gas that comes before sulfur on the periodic table. So neon is 10, sulfur is 16, 10, 11, 12, 13, 14, 15, 16. So in this instance, I can write neon, okay, and we know that neon ends 2p6. So what comes after 2p6 is going to be 3s2, and then whatever comes after that is going to be 3p, and it's going to be 3p4. And if I'm going to write the orbital notation, I'm still going to write neon. I'm going to write 3s, and because the S has got 2 electrons, it's going to go arrow up, arrow down. I'm going to write the 3 different orientations of P. And then I'm going to go arrow up, arrow up, arrow up, and then arrow down to get to my 3p4. So at this point, I've now written the noble gas shortcut for sulfur by using neon, which really means 1s2, 2s2, 2p6, and then just finished it after that. The way we determine the number of valence electrons is still the same. We look for the highest energy level, which in this case is the 3. 2 plus 4 is 6. All right, we're going to try one that does not use neon as its noble gas for the shortcut. So we're going to try cobalt. To help you out, cobalt has 27 electrons. I would like you to try cobalt real quick once, please. So with cobalt being element number 27 on the periodic table, if I go back up here and I locate cobalt, the first thing I can do is I see that it's in the D block. I see that it's in the row that we call the 3D, and I see that it's 7 columns over. So I'm going to predict that cobalt is going to be like a 3D7. I see that the noble gas, that is the noble gas in the row directly above it, is argon. And I see that argon would end 3p6. So when I put argon in brackets, I know that I'm ending with 3p6. What comes after 3p6 is 4s, and I can fill that with 4s2. 4s2. After 4s comes the 3d shape, and the 3d shape has 7 electrons in it, so it's 3d7. So then I drew my orbital notation: 4s, arrow up, arrow down; 3d, arrow up, arrow up, arrow up, arrow up, arrow up; 3d down, arrow down, arrow down. So then I ended up with that drawing. And then the number of valence electrons, the biggest energy level is 4. And there's 2 electrons in the 4th energy level. So that's how I got that. Any questions about noble gas shortcut? Yes?
Do you have to put 3D under every orientation?
So the question is, do you have to put 3D under every orientation? And the answer to that question is no. But I'm doing it because it makes sense to me. But the way that the only caution that I would write if you just wrote 3D under one of them and then 5 dashes is sometimes what I see when students do that is you don't differentiate. So it's just it's like 4S and then a whole bunch of dashes, and it all looks like it's the same thing. So if you're going to do that, which I'm totally for, make sure that there's spacing so that the grader can see it. Okay. Any other questions about electron configuration noble gas shortcut? All right. Next thing we need to talk about is photoelectron spectroscopy. And photoelectron spectroscopy has another, it can become an acronym PES. Now, what we do with photoelectron spectroscopy is we take a sample of an element, we put it into a machine, the machine vaporizes that element, makes it into a liquid, and then eventually into a gas, and then it takes that gas and it ionizes it, and then it puts it through an accelerator, and it shoots that gas through a tube. And when it shoots that gas through a tube, the gas has to travel along a bend around the tube. There's a magnet that surrounds that bend, and the more electrons that an atom has, the closer it will bend toward the magnet. And so where the atoms are and where they are detected on the plate at the end of the bend is basically how far or how many electrons it has. And from that, we get some information we can use to identify an electron configuration based on spectroscopy data. So here is what a spectroscopy the X and Y axis graph might look like. And what you need to recognize is that at the origin right here would be where the nucleus is. And then as you go towards the right, you get further and further away from the nucleus. So we have increasing energy levels. The closer you are to the nucleus of an atom, the more difficult it is to take an electron away. The further you are from the nucleus of the atom, the easier it is to take an electron away. I like to think about it when it's morning time and you're in your bed and you're laying in your bed. It requires a lot of energy to get yourself out of bed, especially this week. You know what I'm talking about? But then once you're out of bed and you're like walking toward the bathroom or something like that, it becomes a little bit easier to get away from the bed, right? You know what I'm talking about? No? Maybe? Okay. Now, we're going to compare some data for a bunch of elements and try to figure out how this works. So hydrogen from the periodic table we know has 1 electron, and helium from the periodic table we know has 2 electrons. So if we look at our data, the data for hydrogen has 1 peak. And that 1 peak hits the 1 electron bar going across the graph, right? So that tells me that this element is truthfully hydrogen because it has 1 electron in it. And 2, it tells me a bit about where that electron is located. And that electron happens to be located pretty close to the nucleus because it's the first peak. And so that leads me to believe that the electron configuration for hydrogen is going to be 1s1, which it is. The helium one has 1 peak as well. And that 1 peak is located, it reaches the second or 2 electron bar. So that leads me to believe that it's going to be like S2. But specifically, because there's only 1 peak, it's going to be a 1s2. So that tells me that the electron configuration for helium is going to simply be 1s2. Now, it does get a little bit more complicated. So the next slide that I have has helium being compared with my favorite element, which is lithium. So helium, we've already said, has 2 electrons. Lithium, I'm telling you, has 3 electrons according to the periodic table. Helium's 2 electrons, or that 1 peak, helium has 1 peak, and that 1 peak correlates to having 2 electrons because it's stuck on that 2 electron mark. So that tells me that helium, again, is going to have an electron configuration of 1s2. Now, lithium, on the periodic table, right, helium is in the first row, but lithium is in the second row. And there happen to be 2 peaks on this data set. The first peak has 2 electrons, which leads me to believe it would be like a 1s2. But the second peak has 1 electron. And that would lead me to believe it's a 2s1. So if I write the electron configuration for lithium, it would be 1s2, 2s1. Which kind of makes sense because if lithium is the first element in the second row on the periodic table, hopefully that makes sense because that would, if you predicted its electron configuration from the periodic table, it would be 2s1. So, to make this not more complicated, but maybe make more sense, we're going to use an unknown element and identify the electron configuration and which element it is.
How come lithium's your favorite one?
How come lithium is my favorite element?
Yeah.
A lot of really important uses. It's also just, I don't know. I just always liked lithium. Anyway, so here we have an element that has 3 peaks. Okay? And the first peak has 2 electrons in it, or it has hit 2 electrons. Okay? So I'm gonna think that that's a 1s2. The second peak has 2 electrons also. So I'm going to think that that's going to be a 2s2. Now the third peak has 3 electrons. And so what shape can hold 3 or more?
P.
The P, right? So that leads me to believe that it's going to have 3 electrons. It's probably going to be like a 2p3. So if I clean this up and I write the electron configuration, I get 1s2, 2s2, 2p3. And with that information, can I locate an element on the periodic table that is 1s2, 2s2, 2p3? I would go to the second row. I would go over to the P block of the second row. I would go 3 over, and I would see that it is nitrogen. So what I want you to do is I want you to try to figure out the identity of the element in this graph. So I saw that the first peak hit the bar of 2 electrons, so I thought it was a 1s2. The second peak hit the bar of 2 electrons, so it was a 2s2. The third peak hit the bar with 6 electrons, so 2p6. And the fourth peak hit the bar with 1 electron, so 3s1. So the element that I decided that was going to be was sodium, because it's 1s2, 2s2, 2p6, 3s1. Questions?